3,000 miles beneath your feet, something just moved that shouldn't have. Seismic waves travelling through the centre of our planet came back carrying a message scientists had never decoded before. The inner core, a ball of iron the size of the moon, is slowing, tilting, and now quietly changing shape. Its magnetic shield above us is thinning in places. Precious metals are rising through volcanic rock. A hidden state of matter has been caught flowing where nothing should flow. You are about to descend through every layer of this mystery, from the first broken signal to the weak spot already swallowing satellite signals, to the deepest question we have never been allowed to ask. If this grips you the way it gripped the researchers who found it, hit that subscribe button and stay close. The pressure is building, the clock is shifting. Let's begin. A seismologist sat at his desk in Los Angeles, staring at a line of data that did not make sense. The wave had travelled from a small chain of icy islands near Antarctica, punched straight through the centre of our planet, and emerged on the other side of the world at a quiet sensor array in northern Canada. It should have looked familiar. It did not. Something inside the data was off, and it was off in a way that had no clean explanation. The scientist is John Vidal of the University of Southern California. The sensor array is called Yellowknife, tucked into the cold flatlands above the Canadian tree line. For more than 30 years, Yellowknife has recorded earthquakes rumbling up from the South Sandwich Islands, a volcanic chain so remote that ships rarely pass it. Each earthquake sends vibrations that slice through the Earth's deepest regions, including the solid iron ball at the centre. When the same fault breaks in the same place, the waves are supposed to arrive looking almost identical every time. They are a kind of fingerprint. But this fingerprint had changed. Vidal refined the data, cleaned it, filtered it, then ran it again. The anomaly held. Waves recorded years apart from nearly identical quakes now carried small but unmistakable differences. The shift was tiny. A whisper compared to the scale of a planet, yet it was real. It was reproducible, and it was coming from the deepest part of Earth we can measure. He later admitted, in a tone that rarely slips into scientific writing, that the dataset confounded him. That single word matters. Confounded from a career seismologist means the familiar tools no longer explained what the planet was doing. Here is why that is alarming in the quiet way science can be alarming. The inner core was supposed to be stable. Textbooks have described it for decades as a solid iron sphere, slowly growing, roughly frozen in shape, rotating in a predictable pattern. For most of human history, no one believed anything inside it could change on a timescale shorter than 1 million years. We thought we had a long, patient furnace down there, steady, silent, beyond our reach. The Yellowknife signal said otherwise. Something at the edge of that iron ball was shifting within the span of a human life. Not in geological eras, not in epochs, in years. Measurable, recordable, repeatable years. And the fact that only Yellowknife caught it while a nearby array in Alaska did not was even stranger, because the two arrays listened to slightly different paths through the core. One graze, one plunge. The graze array saw the change. The plunge array did not. That pattern narrows the source of the disturbance to the shallow outer layer of the inner core itself. In other words, the skin of Earth's iron heart is moving. Vidal and his team would go on to publish this in Nature Geoscience in February 2025, after nearly 30 years of compiled seismic data. It would rewrite what we thought we knew about the deepest part of our planet. But before any of that, before the papers, before the press, there was just one line of data on one screen that refused to match its own past. And that line was only the first clue. The object at the centre of our planet is a solid ball of iron the size of the Moon, pressed into a sphere by the weight of everything above it. Its radius is about 759 miles. It sits roughly 3,000 miles below our feet, locked in place by gravity. And despite being the most important object for life on Earth, no human, no drill, no probe, no camera has ever touched it or ever will. Think about that for a moment. We've landed rovers on Mars. We've flown a probe through the outer atmosphere of our star. We've photographed galaxies 13 billion light-years away. But we've never directly observed the thing at the centre of our own world. Everything we know about the inner core has been inferred, calculated, or reconstructed from indirect signals. This is not because we don't want to look. It is because nothing we build can survive the journey. The deepest hole ever drilled by humans reached around 7.5 miles into the crust, before the rock turned plastic from heat and the drill bit began to soften. The Kola Super Deep borehole in Russia hit temperatures far above what was expected and had to be abandoned. 7.5 miles. The inner core sits 400 times deeper than that. To reach it, a probe would need to pass through rock that flows like tar, then through molten metal so hot it glows white, then arrive at pressures more than 3 million times the pressure at sea level. Nothing survives that. Not a ceramic, not a diamond, not anything we know how to build. So how do we know anything about it at all? We listen. Every earthquake is an accidental gift to seismology. When a fault slips, it releases waves of energy that travel through the entire planet, bending, reflecting, and refracting as they pass through layers of different density. Some of those waves pass straight through the core. When they come out the other side, they carry information about everything they touched on the way. Density, temperature, structure, speed of travel, even whether the material was flowing or rigid. It is a form of medical imaging, but for a planet. Instead of X-rays, we use vibrations. Instead of a scanner, we use the global network of seismometers strung across continents and oceans. And the inner core, silent and unreachable, finally speaks through those ripples. That is how we learned, in 1936, that the inner core even exists. A Danish seismologist named Inge Lehmann noticed that earthquake waves were reaching places they should not reach. The only explanation was a hidden solid body buried deep inside what everyone had assumed was molten. She was right. The iron heart of our planet had been there the whole time, waiting to be heard. Almost a century later, we are still learning to hear it. And the sounds coming back now in this decade are different from anything Lehmann or the generations after her ever recorded. The fingerprint has changed. But before we trace where it is changing, we need to understand the messengers themselves. The earthquakes that carry the signal, because only one small cluster of quakes in one frozen corner of the planet has been reliable enough to tell us anything at all. Every clue we have about the deep interior of Earth rides on a wave that was never meant for us. When a fault breaks somewhere in the world, it releases two main types of seismic energy: pressure waves, which push and compress the rock ahead of them, and shear waves, which shake it side to side. The pressure waves can pass through anything: solid, liquid, even gas. The shear waves cannot. They stop cold when they hit a liquid, because liquid has nothing for them to shake against. This single fact is the reason we know our outer core is molten. In the early 20th century, seismologists noticed that shear waves from distant earthquakes simply vanished when they tried to pass through a certain depth. They were being absorbed, erased, swallowed by something fluid. That vanishing point marked the outer boundary of the core, a liquid ocean of iron trapped thousands of miles below the crust. Pressure waves, meanwhile, kept going. They slowed down inside that liquid, then sped up again when they reached something solid at the very centre. That something was the inner core. So the core revealed itself by what it blocked and what it let through. It was the ultimate medical scan, running on energy the Earth provided for free. But there is a catch. To actually map the inner core, you cannot use just any earthquake. You need quakes that repeat, again and again, from nearly the same fault, at nearly the same depth, with nearly the same energy. Because only by comparing two almost identical events, years apart, can you detect a change in the deep material the waves passed through. If the fault slips differently, the signal shifts for reasons that have nothing to do with the core. You're no longer measuring the planet, you're measuring noise. This is why most of the world's seismic data is useless for tracking the inner core. There are, however, a handful of rare places on Earth where the same seismic fingerprint repeats almost perfectly over decades. One of them lies near the South Sandwich Islands, a string of volcanic specks in the cold waters below Argentina. It is one of the most seismically active zones on the planet. The ground there breaks along the same fault patterns again and again, producing what scientists call repeating earthquakes, or doublets. Some doublets match each other so precisely that the only difference between their arrival at a distant sensor must come from something the wave passed through on its way. Something like the inner core. Vidal's team collected more than 120 of these doublets, stretching from 1991 all the way to 2024. They paired them in time, they lined up the waveforms, they looked for ghosts in the signal, and they compared how those waves arrived at two distant listening posts, one near Fairbanks, Alaska, where the wave dives deep into the inner core, and one near Yellowknife, Canada, where the wave only grazes the outer shell of the inner core on its way through. That choice of geometry would turn out to be everything, because the Fairbanks signal stayed mostly clean, the Yellowknife signal did not. And in the difference between those two records, a hidden movement inside the Earth finally became visible for the first time. The messengers had arrived. Now came the message. The South Sandwich Islands are some of the most inhospitable land on Earth. Black volcanic cliffs rising out of frigid ocean. No permanent human population. Winds that can flatten a ship. Ice fog so thick the islands vanish for weeks at a time. You would never guess that this storm-battered arc is also the most important listening post we have ever accidentally built. Beneath those islands, a tectonic plate is being dragged downward into the mantle at a rate of about 3 inches per year. That may not sound dramatic, but sustained over millions of years, it builds up stress that the rock cannot hold forever. The rock breaks, the fault slips, and an earthquake rolls out through the planet. Because the geometry of this subduction zone stays consistent, the quakes happen again and again in nearly the same places, with nearly the same motion. That is the repeating part. That is what makes them usable. Every doublet pair is like striking the same tuning fork twice, decades apart, then comparing the tone. If the tone has shifted, something in the path between the fork and the ear has changed. And the path, in this case, runs through the molten outer core and the solid inner core of our planet. The scientific community has known about these repeating quakes for years. What they did not have, until recently, was enough of them across enough time to track a pattern in the deep earth. Vidal's team solved that by going back decades. They pulled records from Soviet nuclear tests conducted in the early 1970s. They pulled French and American test data from around the same period. They added every well-documented South Sandwich doublet since 1991. Altogether, they assembled the longest, cleanest ledger of deep Earth vibrations ever compiled. Then they did something no one had done before. They used pairs of earthquakes that occurred during moments when the inner core had supposedly returned to the same position after years of drifting. If the core truly was a rigid, unchanging sphere, the waveforms from those matched moments should overlap perfectly, like two copies of the same signature. They did not. At Yellowknife, 10 of those doublets showed small but real differences the rotation alone could not explain. Something else had moved. Something had changed shape. And here is the key detail. The waves at Yellowknife only graze the outer edge of the inner core. The waves at Fairbanks drive deep into it. Fairbanks saw no strange differences. Yellowknife saw them clearly. That is a signature. That narrows the disturbance to the shallow skin of the inner core, not its interior. This is the equivalent of listening for a heartbeat and realizing the shape of the heart itself has changed, while the deeper chambers remain steady. The South Sandwich quakes, the Soviet test blasts, the cold sensors in the Canadian North. None of them were built with any of this in mind. They are, in a sense, the most accidental scientific instrument humanity has ever wielded. And through that instrument, a message finally came through. The message was clear. The inner core was not the frozen stable object we had painted in every textbook. It was alive in ways no one had predicted. And the first sign of that life was a sudden, unprecedented change in its rhythm. For most of the modern geology, we believe the inner core spun at roughly the same rate as the rest of the planet. A little faster, a little slower, but always close, always together. It was like a wheel inside a wheel, locked into the broader spin of Earth, with only minor variations we could barely detect. Then, around the year 2010, that agreement broke. The inner core began turning slower than the mantle and crust above it. Not by much. In fact, the difference was so small that it took more than a decade of additional data and a second careful study to confirm it. But the slowdown was real. It was measurable across multiple repeating earthquake pairs, and it marked the first confirmed change in inner core rotation in several decades. To understand why that matters, you have to understand what the inner core is doing inside the rest of the planet. It is not glued to the mantle. It sits inside the molten outer core like a solid iron ball suspended in liquid metal. Gravity holds it in the middle. But the liquid around it is churning constantly, stirred by heat from below and the spin of the Earth itself. That churning drags on the inner core and can push it forward or pull it backward relative to the rest of the world. For a long time in the late 20th century, the inner core was pulling ahead. Superrotation, scientists called it. By some estimates, the core had been rotating a small fraction of a degree per year faster than the mantle. Over decades, that adds up. A 2023 study in Nature Geoscience by Yang and Song at Peking University compared seismic records going back to the 1960s and found that the pattern was not a one-way drift. It was an oscillation. The inner core appeared to be swinging back and forth on a cycle lasting roughly 7 decades. Around 2010, that swing reached its edge and reversed. The inner core stopped gaining on the planet, paused, and began falling behind. This is not science fiction or sensational framing. It is what the data shows, and it is the first time in recorded history that humans have caught the rhythm of the core mid-beat. Why 2010? No one knows for sure. The turning point lines up roughly with small but real fluctuations in the length of a day. Yes, the actual day. The time it takes Earth to spin once on its axis. Those fluctuations are tiny, on the order of milliseconds, but they are measured precisely by atomic clocks around the world. When the inner core slows, the mantle must subtly speed up to conserve angular momentum. That speed up shortens the day by fractions of a millisecond. The clock adjustments are invisible to us. They are not invisible to the equipment. Here is what makes that detail haunting. Something at the center of the planet reached the end of its swing, changed direction, and somewhere in the world an atomic clock noticed. A timekeeping device in a quiet lab picked up the echo of a motion 3,000 miles below. That is how deep the connection runs between the core and the surface we live on. But a slowing rotation was only the first act of the story, because soon after, the same team would catch something even stranger. The inner core was not just slowing, it was turning the other way. By 2024, the evidence was unambiguous. The inner core was no longer merely slowing relative to the mantle. It had shifted into a state where it was, in effect, rotating backward compared to the crust above it. Not because it had physically reversed its spin through space. The whole planet is still rotating in the same direction that it has for billions of years. But its rate had fallen below the mantles, which means that if you are somehow standing on the inner core's surface and looking up at the overlying rock, the world above would appear to drift past you in the opposite direction. This is what seismologists mean when they say the inner core is turning backward. It is a shift in relative motion, not a reversal of the planet itself. But it's still deeply strange. For decades, the inner core outran us. Now it lags behind. To catch a change this subtle, Vidal and his colleagues needed something close to statistical proof. A single unusual earthquake pair could be a fluke. 2 could be coincidence. They found 24. That was when, in his own words, the result became inescapable. The slowdown was not an artifact of noisy data or a calibration error, it was the state of the planet. Now step back and feel what this means. A ball of iron the size of the moon, floating inside an ocean of molten metal thousands of miles below your feet, just changed the direction of its relative motion for the first time in many decades. And we caught it. The question scientists started to ask next was unsettling. If this is happening on a roughly 70-year cycle, then the last reversal would have taken place somewhere in the early 1970s. The cycle before that, in the early 1900s. Humans only started building the tools to detect this pattern in the second half of the 20th century. So we have maybe 1.5 cycles of real data. Anything older is guesswork. Which means we're only now, for the very first time, watching this rhythm play out with enough precision to understand it. What is driving it is still debated. The leading idea is that it comes from the gravitational push and pull between the inner core and the dense, uneven bottom layer of the mantle, combined with the drag from the turbulent outer core. These forces tug the inner core slightly one way, then the other. Over decades they build into a wobble. The inner core drifts ahead of the mantle for a while, then falls behind, then catches up again. That explanation sounds tidy. It is not, because the oscillation is only part of what has been observed. The backward rotation alone cannot account for everything Vidal's team saw in the Yellowknife signal. Some of the changes in the seismic waveforms were not consistent with simple rotation at all, which means something beyond motion is at work. Something about the structure of the inner core, its shape, its outer boundary, its skin, appears to be shifting too. And that is where the story stops being about a clock and starts being about a body. A body that, at its very surface, is being reshaped by the raging liquid around it. When the Vidal team looked harder at the Yellowknife data, they realized rotation was only half the answer. Some of the waveform changes they saw between paired earthquakes could be explained by the core turning. Others could not. Those stubborn, unexplained signals pointed to something more fundamental. The surface of the inner core appeared to be deforming, not shattering, not cracking, not melting away. Something softer and stranger. The outermost skin of the inner core, the thin layer where the solid iron meets the molten ocean around it, seemed to be slowly bulging and shifting over time. Imagine a frozen ball suspended in a warm, violent current. The ball remains solid at its heart, but its outer rind, caught in the flow, is being nudged, squeezed, and warped year by the churning liquid pressing against it. This is the kind of change that should not happen on human timescales. For decades, every model treated the inner core as rigid to within a rounding error. Geological change, sure, over millions of years. But not this. Not a shapeshift visible within a single human lifetime. That is not supposed to be possible. And yet it is what the waves keep telling us. Vidal put it simply when the paper came out in Nature Geoscience in February 2025. For the first time, he said, "We are seeing the outer core disturb the inner core." Translated from scientist to plain speech, that means the molten metal ocean above the solid iron ball is now understood to be strong enough, turbulent enough, and close enough to the boundary that it can physically deform its neighbour on a scale of years. The deformation is not uniform, it appears to happen in patches. Some parts of the inner core's surface seem to be bulging outward slightly, others appear smoother. The exact geography of the change is still being mapped, and it will take many more years of seismic data to build a clean picture. But the fact of the change is no longer in serious doubt within the field. Here is why this matters beyond the pure science. The shape of the inner core affects how heat leaves it. That heat is the fuel for everything happening above, including the turbulent flow in the outer core that generates our magnetic field. If the shape of the inner core is actually changing year to year, then the pattern of heat flowing outward from it is also changing year to year, and that means the magnetic dynamo above it is being driven by a source that is no longer perfectly steady. It is as if the furnace at the bottom of the house keeps shifting the position of its flame, and every room upstairs feels the draft differently, even if you cannot see the flame move. For the first time in human history, we have direct seismic evidence that our planet's deepest engine is not a fixed object. It is a living, shifting, deformable sphere, responding in near real time to the chaos of the molten ocean it floats in. A frozen heart that is, in its own slow way, beating. And the force doing the reshaping is the next layer up. A world of liquid metal we're only beginning to understand. Above the solid inner core sits an ocean of molten iron and nickel nearly 1,400 miles thick. This is the outer core. It is the largest reservoir of liquid metal in the solar system that we know of, and it is doing 3 jobs at once. It conducts heat upward from the inner core into the mantle. It generates the magnetic field that surrounds the entire planet. And as we are now learning, it is actively sculpting the surface of the solid core below. The outer core is not calm. It never has been. Heat rising from below, combined with the planet's rotation, drives convection currents that twist and spiral through the molten iron. These currents move faster than most people imagine. In some places, the liquid metal flows at speeds of a few miles per year, which is extraordinary for a material that dense under that much pressure. It is fast enough that satellite measurements of the magnetic field above the core can detect flow patterns changing from decade to decade. Now imagine the inner core sitting at the bottom of that metal ocean, with currents of liquid iron rushing past it, around it, pressing against its frozen skin. For decades, we assumed those currents were too weak, or the inner core was too rigid for there to be any direct physical interaction on human timescales. That assumption is what just broke. What Vidal's team caught at Yellowknife is the signature of the liquid metal ocean doing real, measurable work on the solid iron ball inside it. Not eroding it, not melting it, deforming it, nudging it into new shapes as the currents rearrange themselves. This is why the timing matters. The outer core is where our magnetic field is made. If the flow patterns in that liquid metal are shifting strongly enough to bulge the inner core below, they are almost certainly shifting strongly enough to change the magnetic field above. And that is exactly what satellites have been seeing. But to understand why the outer core is so restless in the first place, you have to understand what fuels it. The engine is heat, specifically heat leaving the inner core as iron crystallizes out of the outer core and joins the solid ball at the center. That crystallization releases energy, almost like a planetary scale phase change. It is slow, but it is This process has been running for more than 1 billion years, maybe longer. It is what keeps the outer core stirring and what keeps our magnetic shield alive. So the inner core is growing very slowly by stealing iron from the liquid metal ocean above. The act of growing powers the currents in that ocean. Those currents generate the magnetic field. And those same currents, we now know, are powerful enough to warp the surface of the very thing that feeds them. It is a loop, a feedback system more tightly coupled than we realized. The inner core and outer core are not two quiet layers stacked on top of each other. They are locked in a conversation, and that conversation is what keeps Earth habitable. When one side of the conversation starts behaving differently, the other side will respond. We're beginning to see that response now, both at the surface of the inner core and in the shield we all live under. And the conversation, it turns out, has been going on in cycles for far longer than anyone realized. The inner core does not move chaotically, at least not as far as we can tell. When seismologists Yang and Song published their 2023 analysis in Nature Geoscience, they did something almost no one else had the patience to do. They went back to seismic records from the 1960s, then pulled every usable doublet from the South Sandwich Islands up to the present. Then they looked for a pattern. They found one. The inner core, relative to the mantle, appears to oscillate on a cycle of about 70 years. It drifts slightly faster than the surface for roughly 35 years, then slows, pauses, and drifts slightly slower for the next 35. Around 2010, according to their work, the core completed one of these turnarounds. That is the same moment Vidal's team later confirmed as the start of the current slowdown. 2 independent analyses, same turning point, same cycle. That matters because it suggests this is not a one-time anomaly. It is a heartbeat, a slow, deep, 70-year pulse running through the center of our planet. Here is what makes that both reassuring and unsettling at the same time. Reassuring, because a repeating cycle implies the planet is not suddenly going off the rails. Whatever is happening down there has likely been happening for a very long time, long before we had instruments to catch it. Unsettling, because a 70-year cycle means we have been able to measure at most 1.5 full swings of this rhythm. Our entire scientific understanding of inner core rotation is built on less than a century of data spanning a pattern that might take many cycles to fully reveal itself. In other words, we caught the rhythm mid-song. What drives the pulse is still an open question. The leading explanation involves gravity. The mantle, that thick layer of hot rock between the core and the crust, is not perfectly uniform. It has dense patches and lighter regions, continents of heavy rock, and areas of less dense material. Those density differences exert a subtle gravitational pull on the inner core below. At the same time, the swirling liquid of the outer core pushes on the inner core with its own forces. The two sets of forces fight. They alternate, and the inner core responds by wobbling slowly in its orbit, first ahead, then behind, then ahead again. There may be a second driver too. The length of a day, measured by atomic clocks, also appears to vary on a cycle that lines up suspiciously well with the inner core's motion. Fluctuations of a few milliseconds over decades. This is not random drift. It is coupled. The inner core, the outer core, the mantle, and the surface spin are all talking to each other through angular momentum. When one slows, another compensates. The planet is a closed system, and energy cannot just vanish. So the next time you read that the shortest day ever recorded was in the past few years, remember what that headline is really reporting. An atomic clock somewhere on the surface felt the echo of a 70-year rhythm that began before any of those clocks existed. The inner core is keeping time. It has been keeping time for as long as there has been an Earth. We're only just learning to read the score. July 5th, 2024. That date does not appear in most history books. No major war began. No famous person died. But on that day, Earth completed a full rotation in less time than it had on any other day in modern record keeping. Roughly 1.5 milliseconds shorter than the standard 24-hour reference. It was the shortest day ever measured since atomic clocks became accurate enough to catch such things. Milliseconds, 1,000th of a second. Invisible to everyone except the devices that run the satellites, the internet backbones, and the global timing networks that our modern world quietly depends on. But the reason it happened is anything but trivial. The length of a day is not constant. It fluctuates based on countless factors: ocean currents, atmospheric winds, melting ice, tides, even large earthquakes. All of these shift the distribution of mass on the planet, and when mass moves, the spin rate adjusts. This is basic conservation of angular momentum. If a figure skater pulls her arms in, she spins faster. Earth works the same way. Most of those surface factors have been studied for a long time. They're measured, modelled, and accounted for. But when scientists account for all of them and there is still unexplained variation in the length of a day, the remaining signal has to come from somewhere they cannot directly see. Somewhere deep, the core. Seismic studies, including the inner core slowdown work, line up with length of day measurements in ways that are now becoming hard to dismiss. When the inner core slows its rotation relative to the rest of the planet, the mantle has to subtly speed up to keep the total angular momentum balanced. When the inner core speeds up, the mantle slows. The difference is tiny at any given moment, but over decades it produces measurable patterns in how long a day lasts. What happened in 2024 is consistent with this. The inner core has been decoupling from the mantle since around 2010. The mantle is now running a hair faster than it was, and our clocks, running in labs scattered across the world, caught the result. The International Earth Rotation and Reference System Service, the global body that oversees time standards, has had to add leap seconds to official clocks dozens of times over the past decades to keep civil time aligned with Earth's actual spin. For the first time in the history of that system, scientists are now discussing whether a negative leap second might eventually be needed. A second subtracted from the official clock rather than added. It has never happened, and it would happen because the planet is spinning slightly too fast. The cause of that acceleration is almost certainly in part the thing we just described, a core in transition, an iron ball changing its rhythm, and the mantle above it responding, and the surface absorbing the last faint tremor of that motion. Think about the chain. A ball of iron 3,000 miles below changes its spin. The liquid metal around it rearranges, the mantle adjusts, the crust follows, and somewhere in a quiet vault, a cesium atom vibrates just slightly out of sync with where it should be. We live on a planet whose heartbeat we are only starting to hear. And the next surprise is that the heartbeat may not even be beating in a state of matter we recognize. Everything described so far has assumed that the inner core is a solid ball of iron. That is what the textbooks say. That is what Inge Lehmann concluded in 1936. That is how every scientist has modelled it for nearly a century. In September 2025, a team from Sichuan University and the Chinese Academy of Sciences published a result in National Science Review that quietly pulled the rug out from under that assumption. The inner core, they argue with new experimental evidence, is not a conventional solid at all. It is something stranger, a state of matter called Superionic. Here is the simplest way to picture it. Imagine a metal scaffolding, a rigid lattice of iron atoms locked in place. Now imagine smaller atoms, carbon mostly, slipping between the iron atoms and flowing freely through the lattice like water running through a wire cage. The iron stays solid, it holds its shape, but the carbon inside it moves like a liquid, travelling through the metal as if the metal were not even there. That is Superionic. Part solid, part liquid, both at once, not in different regions, in the same place, at the same time. This was first proposed as a theoretical possibility for the inner core back in 2022, based on computer models. Until recently, nobody had been able to prove it in the lab. The problem was recreating the conditions inside the core. You need pressures of over 3 million atmospheres and temperatures somewhere between 4,000 and 6,000 degrees. No container holds up under that. No furnace reaches there. No ordinary experiment comes close. The Chinese team solved the problem by not using a container at all. They used a cannon, specifically a high-speed shock compression platform that fires a projectile into a target of iron-carbon alloy at speeds near 15,000 miles per hour. For a fraction of a second at the point of impact, the sample reaches roughly 140 gigapascals of pressure and close to 2600 Kelvin. Not quite inner core conditions, but close enough to reveal what the material does when pushed toward them. What it did was soften. Dramatically. The alloy's resistance to shearing dropped far below what any pure solid would show. It started behaving like something between metal and honey. Exactly the kind of behaviour that would match the weird seismic signals the inner core has been producing for decades, signals that scientists have struggled to explain. One of those signals is a very low shear wave velocity. For a material as dense as iron under that much pressure, shear waves should travel fast. Inside the inner core, they travel much slower than expected. It is as if the metal is softer than it has any right to be. Previous theories tried to blame this on strange iron phases or impurities or crystal orientations. None of them fit cleanly. Superionicity fits. It makes the core squishy like butter, rather than rigid like steel, in the memorable phrasing of one researcher. And that softness matches the data. If this holds up under more experiments, it will be the deepest change in our picture of Earth's centre in almost 100 years. The very material at the middle of our planet may not be what we thought it was. It may be moving, flowing and conducting in ways no standard solid ever could, and that changes what it can do for the field above it. The lead author of the Superionic study, Yujun Zhang, used a beautiful image to describe what the carbon atoms are doing inside the inner core. They weave through the iron lattice, he said, the way children move through a square dance. The iron partners stay in place. The carbon partners flow between them, changing position constantly, never settling. That image is more than poetic. It has consequences. When atoms move through a material, they can carry charge. And when charge moves, it can generate electrical current. And when electrical current flows inside a rotating body, it can produce or amplify a magnetic field. This is the fundamental recipe of what is known as the geodynamo, the mechanism that creates our planet's magnetic shield. Until now, the geodynamo has been attributed almost entirely to the molten outer core. The logic was simple. Only the outer core was thought to be liquid. Only a liquid could flow fast enough to produce the currents needed to sustain a magnetic field. The inner core, being frozen solid, was treated as a passive anchor, a dense lump at the center that fed heat upward and nothing else. Superionicity challenges that picture. If the inner core has mobile charged particles moving through it, even if the iron framework is locked in place, then the inner core is not passive anymore. It can contribute to the magnetic field. It can store energy. It can shift patterns of conductivity in ways no solid model would allow. The research team behind the Superionic paper noted this directly. The flow of light elements through the iron lattice may play a role in powering or modulating the geodynamo above. This would help explain a handful of observations that have puzzled researchers for years. The magnetic field is not just a single steady bubble around the planet. It has wiggles, drifts, and patches that change over time. Some of these changes happen faster than the outer core alone should be able to produce. If the inner core is quietly feeding energy into the system through Superionic flow, those faster changes make more sense. There is another possibility that the research opens up. Different mixtures of light elements, carbon, hydrogen, oxygen, silicon, sulfur, may behave differently under Superionic conditions. That means the inner core might not be chemically uniform. Layers, patches, or pockets of different Superionic compositions could exist within it, each conducting heat and charge at slightly different rates. A kind of hidden geology at the center of the planet, built not out of rocks, but out of flowing atomic populations. Earlier this year, a separate paper in Nature Communications from December 2025 proposed something related. A team from the University of Münster and collaborators simulated inner core conditions and found that iron alloys with carbon and silicon could form an onion-like layered structure, each shell behaving slightly differently from the next. Their model aimed to explain seismic anomalies that have long shown the inner core is not the same in every direction. Put the two ideas together and a new picture forms. The inner core may be layered, partly superionic, and actively exchanging energy with the outer core above it. Not a frozen lump, a structured, dynamic, electrically active object. And that changes the stakes of everything happening at the surface of our magnetic shield. Long before anyone suspected the inner core might be superionic, seismologists were already picking up strange signals from it. Seismic waves do not travel through the inner core at the same speed in every direction. They go faster along the rotational axis of the planet, the north-south line, than they do across the equator. The difference is small but clear, and it has been confirmed by decades of observations. That property is called anisotropy, and it has been an embarrassment to simple models of the core for a long time. A uniform ball of iron should behave the same no matter which direction you probe it. The inner core does not, which means it is not uniform, which means it has structure. But what kind? For years, the best theory was that the iron crystals inside the inner core were aligned along a preferred direction, the way a stack of metal grains could be oriented by the pressure and heat of formation. That worked up to a point. But finer measurements revealed that the anisotropy itself changes with depth. The outer layer behaves one way. The deeper you probe, the more the speed patterns shift. It is as if the inner core is built out of concentric shells, each with its own internal orientation. The Münster team's December 2025 paper in Nature Communications tested a new version of this onion idea. They used a powerful synchrotron light source at DZ in Germany to squeeze iron alloys with mixtures of silicon and carbon under inner core pressures and temperatures. They watched how those alloys behaved plastically, how they flowed, bent, and oriented themselves under stress. The result was striking. When iron is mixed with different amounts of carbon and silicon, the alloy forms layers. Different compositions sort themselves into different depths, each with its own crystal alignment and each conducting seismic waves at different speeds. If the inner core formed this way over billions of years, with chemistry evolving as it grew, it would naturally develop an onion structure. Shell after shell, each a slightly different metallic mixture, each seismically distinct. This matches the observed anisotropy pattern almost too well to be a coincidence. Here is the part that matters beyond the physics. If the inner core is layered, then so is the heat flow leaving it. The outer shells release heat into the liquid core differently from the inner shells. Chemistry gradients affect how iron crystallizes out of the outer core and joins the inner one. This means the growth of the inner core itself is not a clean, smooth process. It is directional, patchy, uneven. Some parts grow faster than others, and that unevenness has to show up somewhere above. It shows up in the geomagnetic field. The dynamo in the liquid outer core does not produce a perfect dipole magnet. It produces a field with hotspots of strength and weakness, patches where the field lines dive back into the Earth in the wrong direction, and regions where the magnetic intensity changes much faster than elsewhere. Every one of those patterns is a signature of an uneven driver below, a core where heat and chemistry are not perfectly distributed. We are finally beginning to see why. The inner core is not a smooth ball of frozen iron. It is a layered anisotropic, possibly superionic, slowly deforming structure with regional variations that ripple upward through the liquid metal above and surface in the magnetic field we rely on. Which raises a darker question. How much of that field can we actually count on staying stable? To understand what the magnetic field is defending us from, you have to understand where its energy comes from. It comes from heat. Staggering, almost unimaginable heat, locked at the center of our planet and leaking slowly outward over billions of years. The temperature of the inner core is estimated to be between roughly 10,000 and 13,000 degrees Fahrenheit. For context, the surface of the star that lights our sky is about 10,000 degrees Fahrenheit. The center of our planet is, in round terms, as hot as, or slightly hotter than that surface. Pause on that for a second. 3,000 miles beneath your feet, in a region no human will ever see, a ball of iron glows white hot at temperatures that match or exceed the visible surface of the brightest object in our sky. The reason it stays solid despite that heat is pressure. The weight of everything above, all the mantle rock, all the crust, all the oceans pressing down, squeezes the iron so tightly that it cannot melt. Above a certain pressure, even a white-hot metal behaves as a solid. That boundary, where pressure wins and the material freezes, sits roughly 3,200 miles down. Below that depth, iron is solid. Above it, the pressure loosens just enough, and the same iron becomes liquid, the outer core. So the inner core is a solid only because it is being squeezed harder than it is being heated. Now consider where that heat came from in the first place. Part of it is primordial, leftover warmth from when the Earth formed out of colliding rock and metal 4.5 billion years ago. Part of it comes from the decay of radioactive elements scattered through the mantle and the core itself, mostly uranium, thorium and potassium, still releasing small amounts of energy as they break down over deep time. And part of it comes from a continuous act of freezing. As iron crystallizes out of the liquid outer core and joins the solid inner core, it releases latent heat, the same kind of energy a freezing pond gives off as water turns to ice. That energy flows upward and keeps the outer core churning. The numbers are unsettling in a different way. The inner core is growing at roughly 1 millimeter per year on its radius. That sounds nothing. Scale it. Over 1 billion years, that is 600 miles of new solid iron. The inner core has been expanding slowly for most of Earth's history. It did not exist at all for the first part of the planet's life. It froze into being somewhere around 1 billion to 1.5 billion years ago as the outer core cooled enough to begin crystallizing. Before the inner core existed, Earth's magnetic field ran on different physics. Paleomagnetic records in ancient rocks suggest it was weaker and less stable. Once the inner core started forming, the dynamo in the outer core strengthened, and the field became the reliable shield that eventually allowed complex life to survive on land. In other words, we are here because the inner core started freezing in time. The heat it stores, the heat it releases, the heat it drives upward. All of it is the fuel for the shield above, and now that fuel source is showing signs of change. Pressure at the center of the Earth is not a number most people can picture. At sea level, every square inch of your body is pressed on by about 15 pounds of atmosphere. Most people never notice it because it acts on us evenly from all sides. At the bottom of the deepest ocean trench, Challenger Deep, the pressure rises to about 16,000 pounds per square inch. That is already enough to collapse most engineered vessels in an instant. At the center of our planet, the pressure is roughly 360 gigapascals, or more than 3.5 million atmospheres. That is more than 50 million pounds per square inch. At that level, matter stops behaving the way any of us grew up thinking it should. Iron, which at the surface is a relatively straightforward metal, transforms under such pressure into forms that look almost nothing like what you find in a steel beam. Its crystal structure compresses into a hexagonal arrangement. Its electronic properties change, its ability to conduct heat and charge shifts. Even which elements stay mixed into the metal changes. This is why the Chinese team had to build a cannon to study the inner core. This is why no laboratory on Earth can hold those conditions steady for more than a fraction of a second. This is why every model of the deep Earth carries an asterisk next to it. We are reasoning about matter at the edge of what physics even agrees on. What the pressure does, above all, is refuse to let the iron melt. Despite temperatures rivaling the surface of the nearest star, the iron at the center stays locked in place, because the weight of the planet is pressing it from every direction at once. It is frozen not by cold, but by squeeze. And yet, as the Superionic research is now showing, frozen in this sense does not mean still. The lattice holds, the carbon inside does not. You can have a solid scaffold with a liquid ghost flowing through it. Pressure forces the structure. Heat keeps the smaller atoms mobile. The result is neither familiar solid nor familiar liquid. It is a material regime most of us will never encounter in our lives. That is what sits 3,000 miles below us. The reason this matters for the surface is that all of this pressure and heat combine to set up a specific set of conditions that the rest of the planet is adapted to. The magnetic field strength, the crystallization rate of iron, the flow patterns in the outer core, the slow growth of the inner core, all of them depend on the exact pressure and temperature regime inside. Change any one of those inputs even slightly, and the outputs begin to drift. We are not, as far as anyone can tell, looking at a drastic change in either pressure or temperature at the center. Those move over tens of millions of years, not decades. But we're looking at changes in how heat is distributed across the surface of the inner core, how currents move in the outer core above it, and how the resulting magnetic field propagates to the surface. Small inputs, big outputs, that is the geometry of the problem. And nowhere is that ratio more visible than at the boundary where solid iron meets liquid iron, the most extreme interface on Earth. There is a line inside our planet where solid becomes liquid, where pressure finally loses just enough to let iron melt, where a sphere of frozen metal ends and an ocean of molten metal begins. That line is called the inner core boundary. It sits roughly 3,200 miles below the surface, and it is almost certainly the most turbulent, most violent, and most scientifically confusing boundary inside the Earth. Everything interesting about the core happens here. This is where iron crystallizes out of the liquid and joins the solid. It is where latent heat is released. It is where light elements, carbon, sulfur, oxygen, silicon, are selectively ejected from the freezing metal and swept upward into the liquid core above. It is where the outer core's violent currents meet the comparatively calm inner core. It is where the shape changes Vidal's team detected are almost certainly happening. And yet, seismically, this boundary is a nightmare to study. Unlike the core mantle boundary above it, which produces strong, clean reflections of seismic waves, the inner core boundary is more diffuse. Seismic waves passing through it do not bounce cleanly. They scatter, fade, and sometimes show a transition zone rather than a sharp edge. Some studies have suggested this is because the boundary itself is not uniform. In some places it may be sharp. In others, it may be a mushy zone where iron crystals are still forming, caught between liquid and solid. A mushy zone of crystallizing metal, at the pressure of millions of atmospheres, at the temperature of a star's surface, under the constant shearing of turbulent liquid iron currents above. That is the interface we're trying to map with vibrations from distant earthquakes. Here is why it matters. The act of iron crystallizing at this boundary is the primary engine that drives the outer core's convection, which in turn generates the magnetic field. As iron freezes out of the liquid, it is denser than the lighter elements it leaves behind. Those lighter elements rise. Their rise creates upward currents. Those currents, combined with the planet's rotation, twist into the swirling patterns that produce electricity. The electricity produces magnetism. The magnetism becomes the shield. Every step of that chain starts at the inner core boundary. If the boundary is uneven, the freezing is uneven. If the freezing is uneven, the currents above it are uneven. If the currents are uneven, the magnetic field is uneven. And we see that unevenness plainly every single day in the satellite maps of Earth's field above. The shape changes Vidal detected probably originate right here. Patches where crystallization is happening faster, or where the outer core's turbulence is pushing harder, cause the inner core's outer skin to bulge or shift. Other patches stay smoother. The result is a surface that is not a perfect sphere and that is slowly, year by year, reshaping itself. No one has ever seen this boundary directly. We infer it from scattered vibrations. We model it from shock compression experiments. We guess at its fine structure from theory. And yet, for all that uncertainty, it may be the single most important line inside our planet. Everything we depend on for a habitable surface is powered by what happens at that edge. The next layer up is where that power becomes the shield we live under. Above the boundary, above the liquid metal ocean, above the turbulent currents, something begins that no other rocky planet in our solar system has at anywhere near the same strength. A magnetic field. Invisible. Enormous. Shaped roughly like a giant teardrop wrapped around the Earth, extending tens of thousands of miles into space, deflecting the constant storm of charged particles the nearest star throws at us every second of every day. This is the geodynamo's product, the magnetosphere, and it is the reason there is life on the surface to write about any of this. Without it, we would be in serious trouble. Charged particles from solar activity, travelling at hundreds of miles per second, would slam directly into the atmosphere. They would strip it away over time, the way they have stripped away most of the atmosphere of Mars over billions of years. Mars lost its magnetic field early in its history, probably as its core cooled too much to maintain a dynamo. The result is visible. A thin, cold atmosphere. Brutal radiation at the surface. No liquid water left except in frozen form. Earth escaped that fate because our core kept freezing. Our dynamo kept spinning. Our field kept standing. The field does more than protect us from particles. It protects the atmosphere itself, which in turn protects us from ultraviolet radiation, regulates temperature, and traps the oxygen we breathe. A recent NASA study in 2025 even proposed a long-term statistical link between the strength of Earth's magnetic field and the levels of oxygen in the atmosphere over deep geological time. The two appear to have risen and fallen together. The mechanism is still being investigated, but the correlation over hundreds of millions of years is striking. In other words, the field above us may not just defend breathable air, it may help make breathable air possible. All of this comes from what is happening in the deep core, the freezing at the inner boundary, the convection in the outer core, the electrical currents generated by that convection, the magnetic field produced by those currents. A four-step chain running continuously for over 1 billion years, entirely out of human sight, keeping the surface livable. We did not build it. We did not engineer it. We cannot switch it on if it goes off. And the data now coming in suggests that this chain is not as static as we used to assume. The inner core is changing shape. The outer core's flow patterns are shifting. The magnetic field above is shifting with them, most visibly in places where the shield is already weakest. The most famous of those places is over the southern Atlantic Ocean. It is a region where the field is about 30% weaker than it should be for that latitude. Satellites passing through it routinely glitch. Computers on board the International Space Station reset. Cosmic rays hit harder, and that region has been growing measurably for more than a decade. What is happening in that patch of sky is not a small matter. It is the clearest surface signal we have that something about the core below is in transition, and it deserves a chapter of its own. Because once you know where it is weakening and how fast, the question becomes unavoidable. What happens next? Over a wide stretch of ocean reaching from southern Brazil across to the coasts of southwest Africa, Earth's magnetic field is noticeably weaker than it should be. Not gone, not reversed, just thinner. A soft spot in the otherwise robust shield wrapped around the planet. Scientists have known about this patch since the 19th century. They gave it a plain name, the South Atlantic anomaly. At the surface, no one can feel it. Your compass still works. Your body does not notice anything unusual. The weather patterns above the region behave normally. If you flew through it on a commercial airliner, nothing would change. But at the altitudes where satellites orbit, the anomaly stops being invisible. It becomes a hazard. Inside that region, charged particles from the nearest star, which are normally deflected far above Earth by the magnetic field, are allowed to dip much lower than they do anywhere else. Some of them penetrate deep enough to strike the orbiting hardware we rely on for communication, navigation, weather prediction, and military reconnaissance. When satellite passes through the anomaly, it is essentially flying through a thin patch of the umbrella, where rain leaks through. The European Space Agency has been tracking this patch for decades. Since 2013, it has done so with a dedicated trio of satellites called Swarm. They fly in formation, measuring the planet's magnetic field with extreme precision, catching small changes that older instruments would miss. In October 2025, ESA published the most comprehensive analysis yet of what Swarm has seen during its mission. The news was not reassuring. Between 2014 and 2025, the South Atlantic anomaly expanded in surface area by nearly 1% of the entire Earth. That may sound small, it is not. It is a region comparable to half the size of continental Europe, added onto an already large weak zone over a span of just 11 years. The minimum strength of the field inside the anomaly also dropped. In 2014, the weakest point measured about 22,430 nanotesla. By 2025, it had fallen to roughly 22,094. For a field that normally drifts only slowly over decades, a drop of more than 300 nanotesla in 11 years is sharp. It is not yet catastrophic, but it is measurable, consistent, and accelerating in certain sub-regions. The most important development is that the anomaly is no longer a single smooth weak patch. Since 2020, it has started splitting into two cells. One sits over South America, the other sits in the Atlantic southwest of Africa. Each is weakening on its own timeline, with the African cell now deepening faster than the South American one. The lead author of the study, Chris Finlay of the Technical University of Denmark, described the behaviour as something special happening beneath the region. In plain language, the flow patterns in the liquid outer core directly below that part of the planet are doing something unusual. Field lines that normally exit the planet at that location are in places flowing back into it. These are called reverse flux patches, and they act like small internal leaks that weaken the overall shield. The South Atlantic anomaly is not just a quirk of geography. It is a direct fingerprint of the outer core's behaviour near the core mantle boundary below. And when that fingerprint starts shifting this quickly, it means the fingers underneath are moving. What we see above is only the outer edge of a much deeper disturbance. When the South Atlantic anomaly began to split, it surprised people who had been studying the field for their entire careers. For most of the time that Swarm has been watching, the anomaly behaved as a single large weak zone, roughly oval, slowly drifting westward. The expectation was that it would continue doing exactly that, drift west, grow slowly, eventually cycle back to something more normal. Instead, around 2020, a new minimum began forming off the coast of southwest Africa. The anomaly started pulling itself into two distinct weak centres, like a cell dividing. This is not a subtle change. A single weak patch reflects a single pattern of disturbed flow in the outer core beneath it. Two weak patches reflect two. It means the flow patterns of molten iron deep below are reorganizing into a new configuration. That configuration is still evolving, no one can yet predict where it will stabilise, or whether it will stabilise at all. The African cell, the newer of the two, is the one that has been deepening fastest. Between 2020 and 2025, it weakened more rapidly than any other region on the anomaly map. The current minimum under Southwest Africa has fallen by hundreds of nanotesla in just 5 years, which on geological timescales is practically instantaneous. Whatever is happening in the outer core beneath that stretch of ocean is moving fast by the standards of the deep Earth. There is only one realistic explanation for a change of this kind. The liquid iron below that region is rearranging its flow. Specifically, the pattern of what geophysicists call reverse flux patches is expanding in that area. A reverse flux patch is a spot where, instead of the magnetic field exiting the planet the way it is supposed to, the field lines curl back into the Earth in the wrong direction. It is a small internal short circuit. Individually, these patches are not disasters. They have existed for most of recorded history somewhere on the planet, but the size, number and location of them add up. When many small patches cluster in one region and grow, they weaken the total field strength at the surface above. The South Atlantic anomaly is, at its heart, the visible result of a large cluster of reverse flux patches under one specific stretch of ocean. Since 2014, satellites have watched those patches get bigger, more intense, and more spread out. The expansion is real. The splitting is real. And it points to something the researchers themselves have been hesitant to overstate, but also refuse to brush aside. The dynamo below us is entering a phase we have not watched closely before. Chris Finlay, writing in 2025, made a careful point that is worth understanding. The data does not show any sign of an imminent reversal of Earth's magnetic poles. Nothing in the current measurements predicts a flip, but the data also does not show a simple, smooth return to normal. What it shows is a complex restructuring of the field in specific regions, driven by changes in the outer core flow, changes that are likely connected to the core mantle boundary above the inner core. The weak spot is weakening, the split is widening. And the process is almost certainly tied to the deeper shifts we've been tracking all along. Next, we need to look at what the practical cost of this already is. Not in the distant future, right now. The anomaly is not a theoretical problem. Satellites passing through the South Atlantic anomaly today experience measurable documented damage. This has been happening for decades, but the rate of problems has increased as the region has grown. When a satellite flies through the weak patch, the reduced magnetic shielding allows more high-energy charged particles to reach its electronics. Those particles can flip bits in memory, short out components, reset computers, corrupt data, and occasionally destroy hardware outright. Mission operators plan around this. They turn off sensitive instruments as their spacecraft pass through. They reroute data. They accept that certain parts of the orbit are effectively blind spots. The International Space Station crosses the anomaly multiple times each day. Astronauts have reported phantom flashes of light in their vision when passing through it, caused by cosmic ray particles striking the retina directly. This is not fiction. It is documented. Every mission operations team that sends humans or equipment into low Earth orbit treats the anomaly as a known hazard zone. The Hubble Space Telescope, the Fermi Gamma Ray Space Telescope, the Swift mission. Many Earth observation satellites, all of them routinely shut down or mute certain systems when they fly through the anomaly. NASA has publicly described the region as a hazard for spacecraft and has run detailed studies on how to keep its missions operating safely around it. And now the region is growing, which means the blind spots grow. the exposure time for each passing satellite grows, the total radiation dose for spacecraft operating in low Earth orbit grows. That has direct consequences on the ground. Satellite communications networks, GPS positioning, weather forecasting, scientific imaging, and global internet services all depend on hardware that passes through this region. A satellite that fails is not just a piece of orbital debris, it is a capability lost until a replacement can be built and launched. Those costs are measured in hundreds of millions of dollars per spacecraft. They're also measured in delays to weather warnings, gaps in communications coverage, and interruptions in services most people assume will always be there. None of this is an apocalypse. The anomaly is not going to end civilization, but it is a reminder that what is happening in the core is not only a scientific curiosity, it is touching the infrastructure we live on top of right now, this year. There is a quieter consequence too. The weakening field allows slightly more cosmic radiation to reach the upper atmosphere over the anomaly. Airline pilots and flight crews on polar routes already receive more cosmic radiation than ground workers, and the dose rises when flying over zones of the weaker field strength. For most travellers, the effect is negligible. For airline workers logging tens of thousands of flight hours, it is a real occupational consideration that regulators monitor. And so the deep changes in the core have already reached us. Not through headlines, not through disaster, but through the quiet background of systems that keep modern life running. A weak patch in the shield above the South Atlantic is the closest thing we have to a live feed of what the outer core is doing below. It is a feed that is telling us the flow patterns are not as steady as we used to assume, which brings us back to the deeper question. Is this a temporary wobble, or is it the start of something much larger? To understand the anomaly fully, you have to picture what is happening at the core mantle boundary underneath it. Not in metaphor, in actual fluid dynamics. The outer core below the South Atlantic is doing something unusual. In most regions, the flow patterns of molten iron organize themselves into columns and swirls that produce a magnetic field pointing in the expected direction. South of the equator, field lines exit the planet pointing outward away from the surface. North of the equator, they return into the planet. Below the anomaly, some of that geometry is reversed. Patches of outer core flow are producing local magnetic fields that point the wrong direction relative to the global pattern. Those patches overlap with the background field and subtract from it. Where they subtract, the total field is weaker. This is what a reverse flux patch looks like physically. A region where the churning molten iron is producing small localized magnetic structures that point the opposite way from the main dipole. As they grow and strengthen, they eat into the overall strength of the field at the surface above them. Satellite data from SWARM has mapped these patches in detail over the past decade. They are not random. They tend to cluster at specific longitudes, sit at specific depths, and migrate westward over time. Below the South Atlantic, they are concentrated in ways that match the geography of the anomaly exactly. As the patches have intensified and spread, the anomaly has expanded and split. Why is this happening below the South Atlantic specifically, and not elsewhere? The honest answer is that we do not know with certainty. The leading hypothesis involves the structure of the lower mantle. In a large region below Africa and the southern Atlantic, seismic waves travel differently, indicating a huge province of unusually dense, hot rock. Geophysicists call it a large low-shear velocity province. Some researchers think it acts like a lid over the outer core below it, insulating heat differently from other regions, which in turn changes the flow patterns of molten iron directly underneath. Those altered flow patterns may be the ultimate origin of the reverse flux patches that form the anomaly. If that hypothesis is right, then the South Atlantic anomaly is not a random surface phenomenon. It is a direct fingerprint of a structural feature in the deep mantle that has existed for hundreds of millions of years. The weak spot sits exactly where the lower mantle changes most dramatically, which would explain why it never seems to fully go away, only shift, grow, and shrink over centuries. That framing matters. It suggests the anomaly is a long-term feature of our planet, not a temporary glitch. Its current growth may be part of a natural cycle, in which the reverse flux patches beneath strengthen for a period, then weaken again. Or it may be part of a longer, slower trend tied to changes in the deeper core. Either way, the signal at the surface is telling us something about the flow patterns 1,000 miles and more below. Those patterns are not static. They are responding to the geometry of the lower mantle above them, and plausibly to the structural changes we are now seeing at the inner core's surface below them. This is the full picture the new data is forcing on us. Every layer is talking to every other layer. The anomaly is not an isolated feature, it is a signal from the whole system, and the question it raises most urgently is whether this system is drifting toward a rarer, bigger event. Every time the magnetic field weakens visibly in one region, someone asks the question, is this the beginning of a geomagnetic reversal, a pole flip? The north and south magnetic poles swapping places, with the field collapsing, reforming, and pointing the other way. It is a legitimate question. It has happened many times in the geological past. Rocks on the ocean floor preserve a permanent record of it. As new crust forms at mid-ocean ridges and cools, iron-bearing minerals align themselves to the magnetic field of the day. The result is a striped pattern of alternating magnetic directions spreading outward from every ridge. Each stripe corresponds to a period when the field pointed one way. The next stripe records the period when it pointed the other way. Reading those stripes, geophysicists have mapped the history of the field going back hundreds of millions of years. Reversals happen irregularly. Sometimes a few times in 1,000,000 years. Sometimes the field holds steady for tens of millions of years before flipping. The most recent complete reversal was about 780,000 years ago, an event called the Brunhes-Matuyama reversal. Since then, the field has held roughly the orientation we know today, though with a few partial excursions where it weakened significantly before recovering. So the question is reasonable. Could the weakening we are now seeing in the South Atlantic anomaly be the beginning of a new reversal? The answer scientists are willing to give in public is specific, and it is worth quoting carefully. The Swarm team and the broader research community have looked at the current data and stated that there is no sign of an imminent reversal. The field strength is not collapsing globally. The overall dipole is still intact. The changes are regional, not planet-wide. Even if they continued at current rates, a full reversal would take much longer to develop than the decade of data we now have. That is the cautious, honest, evidence-based answer, and it is worth trusting on its own terms. But here is what the same researchers also say, quietly, in papers and interviews. Reversals are almost always preceded by long periods of weakening and reorganization of the field. A full flip does not happen suddenly. It happens over thousands of years, during which the field gets weaker, more chaotic, and more complicated, before finally reforming in the new orientation. The South Atlantic anomaly, depending on how you interpret the data, could be either a temporary regional fluctuation or the very earliest stage of a much longer process. We cannot tell which it is. Not yet, not with the data we have. What we can say is that the global dipole strength has been measurably decreasing for more than a century. Since about 1850, it has dropped by roughly 9%. That decrease is not uniform. Some regions have gotten stronger. Overall, the average has fallen. If that trend continues for another several centuries, the field will be weak enough that an excursion or partial reversal becomes a serious possibility. If it reverses, the transition could take centuries to thousands of years. It is not an overnight catastrophe, but it is not nothing either. The honest framing is this: the magnetic field is shifting in ways that have serious practical effects now, and that may, over centuries, lead somewhere unfamiliar. And underneath it all, the core itself is behaving in ways we did not know it could. To understand the stakes of that possibility, it helps to look at what the last reversal actually did to the planet. 780,000 years ago, the magnetic north and magnetic south of our planet swapped places. The transition is preserved in the rock record and has been studied in detail. Its name, the Brunnes-Matuyama boundary, marks one of the most well-documented reversals we have. The reversal did not happen in a day. The best estimates suggest it took somewhere between a few thousand and about 20,000 years for the field to fully reorient. During that transition, the strength of the dipole field dropped to a small fraction of its normal value. Some estimates put the weakest phase at about 10% of the field strength we experience today. During that period, the field was not simply weaker, it was also more chaotic. Multiple magnetic poles appeared in different parts of the world simultaneously. Compasses, had they existed, would have given different answers in different places. What did this mean for the planet at the surface? That is where the science gets careful. There is no clear evidence in the fossil record of a mass extinction tied to the Brunhes-Matuyama reversal. Early humans were already living at that time, and they survived it. Broader life on Earth continued. Whatever happened during the transition, it was not a planetary extinction event. That is reassuring. It is also not the whole picture. During a reversal, the magnetic shield would be degraded globally, not just in one region. The atmosphere would receive more solar and cosmic radiation than it does today. Ozone levels at high altitudes might fluctuate. Certain types of organisms that rely on the field for navigation, like some migratory birds, sea turtles, and certain deep-sea species, could be confused during the transition. Satellites, power grids, and radio communications, all of which depend on a predictable magnetic environment, would experience significantly more disruption than they do now. Modern humans have never lived through a full reversal. Our entire recorded history, roughly 10,000 years, has unfolded during a period of stable orientation. Every piece of technology we have built, every infrastructure system we depend on, has been engineered for a world with the field pointing the way it currently points. A partial reversal, called an excursion, is more common in the record. During an excursion, the field weakens dramatically and may briefly flip before returning to its original orientation. The most recent known excursion, called the Lachamps event, happened about 41,000 years ago. It lasted a few hundred to a few thousand years. During that time, some studies suggest that cosmic radiation levels at the surface rose enough to cause measurable environmental effects, including possibly contributing to changes in atmospheric chemistry. Other researchers dispute the severity of those effects. This is the honest state of the evidence. Reversals happen, excursions happen, life has survived them. But modern civilization has not experienced one, and our infrastructure is not built to weather one gracefully. And here is the connection that matters. The energy for the field comes from the core, The changes we see in the field now are being driven by changes in the core. If the core is entering a new phase of activity, as the inner core slowdown, shape change and Superionic evidence all suggest, then the surface consequences will follow. Not suddenly, not dramatically, slowly, across decades and centuries in ways we're only now learning to read. And while all of that unfolds above us, something else has been quietly happening below. The core, we're now realizing, is not fully sealed off from the planet above. It is leaking. For most of the history of geology, the core was assumed to be a closed system, sealed off from the mantle above it by a sharp physical boundary, locked in place by its own density and utterly unreachable from the surface. The iron and precious metals it contained were thought to be permanently stored there, inaccessible to any process we could detect. In May 2025, a team led by geochemist Niels Messling at the University of Göttingen published a paper in Nature that quietly broke that assumption. They'd been studying basalt samples from the Hawaiian Islands, volcanic rock taken from places like Kilauea, Iki, Kauai, and deep underwater seamounts. Hawaii is special because its volcanoes sit above a mantle plume, a column of hot rock rising from very deep inside the planet. Some researchers have long suspected these plumes might tap material from near the core mantle boundary. If so, the lavas they produce should carry chemical fingerprints from those depths. Messling's team focused on the element ruthenium, specifically on isotopes of ruthenium, which are produced in extremely small ratios that can be used to trace the origin of a rock. Ruthenium is part of a family of elements called siderophiles, which are iron-loving. When the Earth formed and differentiated, most of the planet's ruthenium sank along with the iron into the core. Very little was left behind in the mantle or crust. If you find an unusual ruthenium isotope signature in a surface rock, and that signature matches what you would expect from deep primordial material rather than surface material, you have found something that should not be there. They found it. Hawaiian lavas contained trace ruthenium signatures distinct from ordinary mantle rocks. The isotope ratios matched what geochemists expect from the core mantle boundary. The signal was tiny, a few parts per 100,000, picked up with new analytical techniques that had not existed a decade ago. But it was statistically solid, and it was reproducible across multiple samples. Messling, in his own words, described the moment the data came in as realizing the team had literally struck gold. Their data confirmed that material from the core, including gold and other precious metals, is leaking into the mantle above. This is not fast. The leakage happens over geological timescales. Models suggest that adding less than 0.25% of core material to mantle rock is enough to explain the isotope signatures observed. That small fraction is extraordinary, because the mantle is vast and mantle plumes are slow. To detect any core-derived material at the surface at all means the process has been running for a very long time, and that mantle plumes are efficient enough to bring it up. Tungsten isotopes tell a similar story. Researchers have found tungsten signatures in ocean island basalts that preserve chemical clues from the first 60 million years of solar system history. Those clues are consistent with material that spent most of its life sealed in the core before rising slowly through mantle plumes. Combined with the ruthenium data, the evidence is becoming very difficult to explain any other way. The implication is quiet but profound. The core is not a locked vault. It is a slowly leaking reservoir, exchanging material with the mantle above across spans of hundreds of millions of years. We are the first generation with instruments sensitive enough to read that exchange in volcanic rocks, and Hawaii is just the beginning. The specific rocks that gave up this secret came from very ordinary-looking places. A drill core from the Kilauea Iki lava lake, which erupted in 1959 and cooled for decades afterward. Basalt sampled from deep-sea volcanoes off the coast of Hawaii by submersibles. Volcanic rocks from the older Hawaiian islands of Kauai and Oahu. Nothing about them looks special to the eye. Dark, dense, fine-grained igneous rock. The same material you find in any hotspot volcano on Earth. But under the right analytical techniques, these rocks carry a fingerprint that traces back nearly 3,000 miles below. The way Messling's team worked with them was brute chemistry. They took about 1 pound of rock, crushed it into powder, then melted the powder in a furnace with carefully chosen chemicals designed to isolate ruthenium. The ruthenium was then passed through a mass spectrometer so precise that it could separate isotopes differing by only a few atomic mass units. The difference between ordinary mantle ruthenium and core-derived ruthenium is measured in parts per 100,000. The technique had to be refined enough to catch that. When the first samples came back with the isotope signature elevated above typical mantle values, the team repeated the analysis on multiple samples from different locations across Hawaii. The signature held. In one sample from Kauai, the ratio was measured at about 0.17, with an uncertainty of about 0.13. That sounds like a tiny number, and it is, but statistically it is meaningfully different from the mantle's normal value. That difference is what allowed the team to claim, with confidence, that some fraction of the rock's chemistry originated at the core mantle boundary. What this tells us about the planet is striking. Hawaii's mantle plume, and probably other plumes around the world like Iceland, the Galapagos and Réunion, are slow conveyor belts of deep material. They rise from the core mantle boundary, carrying with them small traces of primordial chemistry. By the time they reach the surface and erupt, that chemistry has been diluted enormously by the surrounding mantle rock, but not erased. The timescale of this process is important. Messling's team estimates it takes somewhere between 500 million and 1 billion years for material to travel from the core mantle boundary up through the mantle in a plume. One full trip. That means the ruthenium in today's Hawaiian lava began its journey around the time complex multicellular life first evolved, or earlier. It rode slowly upward for 500 million years or more, and only now reached the surface where humans could sample it. That rhythm is longer than any human civilization, longer than any species of mammal, longer in most cases than most geological periods on the standard timescale, and yet it is still fast enough, relative to Earth's age, that the process has happened many times over the life of the planet. Some of the gold that humans have mined in our history may therefore have originated in the core, moved slowly upward over geological time, incorporated into surface rocks, concentrated in mineral veins, and eventually brought to the surface by erosion or volcanic processes. We cannot separate core gold from mantle gold by sight, but at the isotopic level, a small contribution from the deep interior is now becoming traceable. The planet is recycling its own heart into its surface, slowly, constantly, and we're only now catching up. Before ruthenium and tungsten became traces, there was helium, specifically helium-3. Helium has two stable isotopes. Helium-4 is common, produced by the radioactive decay of heavier elements like uranium and thorium in the crust and mantle. Helium-3 is rare. It is a relic isotope formed mostly during the earliest moments of the universe and during the formation of the solar system. There is very little of it produced on Earth today, and any helium-3 that reaches the atmosphere escapes into space almost immediately because of its low mass. So if you find helium-3 in volcanic rock at the surface, it has to have come from somewhere deep, some ancient reservoir that has held it since the Earth was young, somehow still exchanging material with the surface. In the late 1970s, geoscientists began detecting elevated helium-3 in lava from mid-ocean ridges and volcanic hotspots. The ratio of helium-3 to helium-4 in these rocks was higher than anywhere else on Earth. This signal was clear. Something deep was still holding on to primordial helium. The question was where. Two main candidates emerged: a deep, undisturbed region of the lower mantle, or the core. For decades, the question was hotly debated. Helium-3 alone could not settle it. Both deep mantle reservoirs and the core could, in principle, store primordial helium. But then, in the early 2020s, a team working on rocks from Baffin Island in the Canadian Arctic reported some of the highest helium-3 ratios ever measured in terrestrial material. That hint, combined with the new ruthenium and tungsten results from Hawaii, began pointing researchers in a consistent direction. The core, it seems, is probably the source, or at least a major source. Why does this matter beyond the chemistry? Because it fundamentally changes our picture of how the planet works. For a long time, the dominant model held that the core and mantle exchanged heat but not material. The core was energetic but sealed. The mantle was dynamic but separate. Convection currents stopped at the core-mantle boundary. Nothing crossed. The helium-3 data said otherwise, long before the ruthenium data arrived. Something was crossing, slowly, patchily, in small amounts, but unmistakably. And the only place the primordial helium could plausibly come from was deep material that had been locked up since the Earth's formation. The core was the strongest candidate. What this implies is that there is a thin, slow exchange mechanism between the core and the lower mantle, possibly driven by the same processes that generate mantle plumes, possibly linked to the chemical layering at the core mantle boundary itself. The details are still being worked out, but the basic conclusion is becoming increasingly difficult to avoid. The core is not a locked chamber. It has small, slow pores. Material passes from it into the mantle over timescales of hundreds of millions of years. Precious metals, helium, probably other elements we have not yet been able to detect with enough precision. Which means everything we thought we knew about how isolated the centre of our planet is needs to be revisited, and it means that our surface, at a microscopic level, is built partly from material that once sat at the boundary with a ball of iron 3,000 miles below. The scale of that exchange is the next part of the story. How much material is actually moving from the core to the surface? It is a question that sounds almost impossible to answer, but researchers have done the math, and the numbers are sobering in a quiet way. To produce the ruthenium and tungsten isotope signatures observed in Hawaiian lavas, the mantle plume feeding those volcanoes must carry something less than 0.25% of core-derived material. That is the maximum. Probably the real fraction is smaller. But across the vast volume of rock that forms a single volcanic island chain, over geological time, even a fraction of a percent adds up to enormous tonnage. Estimates from the Nature 2025 study suggest that hundreds of quadrillion metric tons of mantle material rise through the plumes that feed ocean islands like Hawaii, Iceland, and the Galapagos. A tiny slice of that has traceable core origins. The total mass of core-derived material delivered to the mantle across the entire history of plume activity on Earth is staggering in absolute terms, even if it is tiny relative to the mass of the core itself. What this means practically is that mantle plumes are not cosmetic features. They are the main conduit by which the deep planet interacts with the surface planet. and the fact that even a thin trickle of core material can be detected in their output tells us that the conduit has been active for a very long time. The speed of the flow is slow beyond human intuition. Mantle rock moves in plumes at rates of perhaps a few centimetres to a few tens of centimetres per year. Over 500 million years, that adds up to enough to carry material from the core mantle boundary all the way to the surface. The journey is longer than most species live, longer than most mountain ranges exist, longer than the lifetime of most stars in some classes. And yet, when we drill into Hawaiian basalt today, some of what we pull out started near the core 500 million years ago. Think about what that means for the Earth's long-term chemical evolution. Over the 4.5 billion year history of the planet, at least several full plume cycles have completed. Each cycle has delivered a small fraction of core material upward. The total accumulated contribution to the mantle is not trivial. It is part of why the mantle today has the composition it does, part of why certain elements are distributed the way they are distributed at the surface. This also has implications for how other rocky planets work. If Earth's core leaks into its mantle, other planets with active plume systems probably do the same. Venus, Mars when it was younger, even large moons with active interiors may all exchange small fractions of their core material with their outer layers over geological time. The process we are now detecting on Earth is probably a general feature of differentiated planetary bodies, but detecting it required a very specific combination of circumstances: stable plume systems, surface volcanism, rocks preserved over long enough periods to sample, and analytical techniques good enough to catch isotope differences at the parts per 100,000 level. All of those converged on Earth in the last decade. We are the first generation to measure the slow leak from the core. And once you start looking, the core begins appearing in places nobody thought to check before. In June 2025, a NASA-led team published a study in Science Advances suggesting something that, on first reading, sounds almost unbelievable. Over the past 500 million years, the strength of Earth's magnetic field has risen and fallen in close correspondence with the levels of oxygen in the atmosphere. The correlation is striking. Both quantities have trended upward since about the start of the Cambrian period, roughly 540 million years ago. Both have experienced dips and peaks at similar times. The relationship is too consistent to be easily dismissed as coincidence. The research team is careful not to claim a direct causal mechanism. Correlation is not proof of causation. But the pattern is there, and it is forcing a conversation the field has not had before. What could possibly link the strength of the magnetic field, generated by churning iron in the core thousands of miles below, with the amount of oxygen in the air we breathe, produced by photosynthesis at the surface? Several hypotheses are on the table. A stronger magnetic field protects the upper atmosphere from being stripped away by solar wind. Less stripping means more of Earth's water vapour, and by extension more of its oxygen, stays in the atmospheric system. Another hypothesis focuses on ozone. The magnetic field helps protect the ozone layer from high-energy particles. A robust ozone layer means more ultraviolet protection for life, which means more thriving photosynthesizers, which means more oxygen. A third hypothesis involves ocean chemistry. The field may influence patterns of ionization in the upper atmosphere, which in turn affect nitrogen fixation and nutrient cycling in ways that ripple into the marine biosphere. None of these mechanisms is fully proven. All of them are plausible, and all of them point to the same deep conclusion. The core is not separate from life. It is linked to it through a chain of physical processes that span the entire planet. This is where the stakes of the recent core changes become unavoidable. If the magnetic field weakens significantly over the next several centuries, and if the NASA proposed link between field strength and atmospheric oxygen is real, then over even longer timescales there could be second-order effects on atmospheric composition. Not in our lifetimes, not even in a century. But over thousands of years, if the field keeps weakening, the connection is subtle, but it is worth sitting with. The iron ball at the centre of our planet is not just something that protects us from radiation. It is, through a chain of processes we are still working out, tied to the chemistry of the air we breathe. That is a different kind of reality than most of us grew up with. The Earth is not a layered object where each layer does its own thing. It is a coupled system where the centre, the middle and the surface are all in conversation. Every finding of the past few years, from the Superionic state of the inner core to the leak of gold in Hawaiian lava, to the weakening shield above the South Atlantic, is a different verse of the same song. We're all, in a sense, living on top of a slow, coupled engine, and the engine has been shifting gears. What that means for the future is the question we have to face now, even without final answers. Step back and think about everything the core provides, without which life on the surface would be impossible or unrecognizable. It provides heat. That heat drives mantle convection, which drives plate tectonics, which shapes continents, recycles carbon through volcanism, builds mountains, opens oceans, and keeps the surface geologically alive. A planet with a cold core is a dead planet. Mars is a case study. Its core cooled long ago. Plate tectonics stopped. Volcanism wound down. Water was stripped away. The surface became the cold, hostile place we see today. It provides the magnetic shield. That shield deflects solar wind, protects the atmosphere from slow erosion, and guards the surface from some fraction of incoming cosmic radiation. Without it, we would face slow atmospheric loss over hundreds of millions of years and much higher surface radiation rates. Mars again demonstrates what happens. Much of the Martian atmosphere has been stripped since the planet's magnetic field collapsed. It provides, as we're now learning, slow chemical exchange with the mantle above. That exchange contributes primordial elements to the surface environment over geological time. It affects the composition of mantle plumes, which in turn affect the chemistry of ocean islands, hotspot volcanism, and the distribution of certain rare elements at the surface. It provides, through its slow crystallization, a time-release energy source that keeps the outer core stirring and the dynamo running for billions of years. Without that steady freezing process, the field would have collapsed long ago. And it provides possibly a long-term link to atmospheric chemistry through the mechanisms the NASA team has begun to outline, a link that may connect the strength of the field to the oxygen we breathe. Take any one of those functions away, and the planet looks different. Take them all away, and it does not support complex life. This is why the recent changes matter. Not because they are a crisis in themselves, they are not. Nothing that is happening in the core right now threatens the surface on any human-relevant timescale. The weakening of the South Atlantic anomaly is a regional issue, not a global one. The slowdown of the inner core is a millisecond-scale effect on the length of a day. The shape changes in the inner core surface are still only visible in high-precision seismic analysis. But the reason these changes matter is what they reveal about the system. They reveal that the core is not static. They reveal that it is coupled to the surface more tightly than anyone assumed. They reveal that the processes we depend on, the heat flow, the magnetic field, the slow exchange with the mantle, are all dynamic systems that can shift, and that we are only now beginning to have the tools to watch them shift in near real time. A living planet is not a frozen machine, it is a breathing system. What the past few years of research have shown, more clearly than any previous decade, is that the breath reaches all the way down to the iron at the centre, and that is, strangely, both humbling and hopeful. Humbling because we realise how little we actually know about our own planet. Hopeful because, for the first time, we have the ability to listen to it in ways previous generations could not even imagine. What we cannot hear yet, though, is still enormous. For all the progress of recent years, our picture of the core remains severely limited. It is worth being honest about where the gaps still are, because those gaps define what the next decade of research must try to fill. The biggest gap is coverage. Almost all reliable inner core seismology relies on a small handful of repeating earthquake sources, the South Sandwich Islands, a few Alaskan subduction zones, some deep earthquakes near Fiji and Tonga. That is it. The vast majority of the Earth's core is probed by seismic waves that only pass through certain slices of it, on their way from source to receiver. Large regions of the inner core have never been sampled directly. We have a partial map, not a full one. This means that when Vidal's team reports shape changes at the near surface of the inner core, they are reporting changes along the specific paths their waves took. Other parts of the inner core could be doing different things, and we would not know. Future progress will require more dense seismic networks, better global coverage, and new data processing techniques that can squeeze more signal out of smaller earthquake sources. The second gap is time. Our useful record of inner core behaviour spans about 60 years at most. If the core operates on a 70-year cycle, we have captured less than one full period. To understand the pattern fully, we need several cycles of data. That means continuing to record, store and analyse seismic signals for decades more. The work we're doing now is foundational for scientists who will be alive long after everyone reading this. The third gap is physics. The conditions inside the inner core are so extreme that no laboratory on Earth can reproduce them steadily. Shock compression experiments like the one that demonstrated the Superionic state can only sustain the conditions for microseconds. Computer simulations rely on quantum calculations that still involve approximations. Every model we build carries uncertainty. As laser-driven compression technology and exascale computing improve, that uncertainty will shrink, but it will not vanish. The fourth gap is the connection to the magnetic field. We can measure the field precisely from satellites. We can model the outer core flow that generates it. But linking surface field changes directly to specific inner core processes is still in its early stages. The Swarm mission has been running for over a decade and has produced the best data we have. Its eventual successor, currently being planned, will push the precision further. New understanding of how the field's small-scale features emerge from deep processes is expected to follow. The fifth gap is the chemistry. We know the core is iron-dominated with some nickel and light elements like carbon, sulfur, oxygen, silicon and hydrogen mixed in. We do not know the exact proportions. Different mixtures produce different properties. The Superionic behaviour depends on what light elements are actually present and in what concentrations. Laboratory studies using high-pressure techniques have narrowed the range, but not closed the question. All of these gaps are tractable, given enough time and investment. None of them will be filled by a single paper or a single mission. They will be filled by decades of cumulative work by hundreds of researchers across dozens of institutions. The pace is slow. The progress is real. We are quite literally in the early chapters of understanding the inside of our own planet. And every decade of new data is bringing surprises that the previous decade could not have predicted. The question is what the next decade may reveal. The decade ahead will likely produce more revelations about the core than the entire century before it. Several lines of research are converging at the same time, and each one reinforces the others. First, seismic networks are expanding. New broadband stations are being installed across Africa, South America, Central Asia, and the Pacific, regions that have long been data poor for deep Earth studies. Ocean bottom seismometers are being deployed in greater numbers to fill in coverage of paths that cross under the Pacific Basin. As these networks come online, the ability to image the core in 3 dimensions will improve dramatically. Second, computational power is reaching scales that allow direct simulation of core mantle boundary processes and outer core dynamo behavior at realistic parameters. Until recently, those simulations had to use simplified physics to run in reasonable time. Now exascale computing is allowing more realistic models that include the full set of relevant equations. These models can be compared directly with observations from swarm and future satellite missions, tightening the link between deep processes and surface measurements. Third, high-pressure experimental techniques are improving. Diamond anvil cells are reaching higher sustained pressures. Dynamic compression experiments, like the ones used to demonstrate the Superionic state, are getting more precise diagnostics. Synchrotron and free electron laser facilities are allowing researchers to probe sample behavior with techniques that were science fiction 20 years ago. The chemistry and physics of the core will be constrained much more tightly in the next decade than in any previous period. Fourth, new satellite missions are being planned to follow swarm. The European Space Agency and NASA have both discussed possible successors that would extend the record of high-precision magnetic measurements. These missions will help determine whether the current trends in the South Atlantic anomaly continue, stabilize, or reverse. They will also help identify any new regions where the field begins changing rapidly. Fifth, the geochemical traces for core leakage will become much more sensitive. Ruthenium and tungsten isotopes at part per 100,000 precision are already revealing patterns. Other isotope systems like osmium, iron, and platinum may soon yield similar insights. The map of where and how core material reaches the surface will become much more detailed. Put all of this together, and the picture that emerges is a discipline on the verge of a new golden age. The core, which for most of the 20th century was considered one of the least accessible objects in science, is becoming one of the most actively studied. And the things we learn about it will have consequences for how we understand planet formation, the evolution of life, the behavior of other rocky worlds, and the long-term future of our own atmosphere. The pace of discovery is not going to slow down. If anything, it is accelerating. The generation of researchers now working with the data being collected this decade will publish papers for the rest of their careers that fundamentally rewrite our understanding of the deep Earth. And for the rest of us, for those not doing the work but living on top of it, there is something worth taking away. The ground under your feet is not a fixed floor. It is the top of a stack of active, responsive, coupled layers, reaching down to a heart of iron that is, in its own slow way, moving and changing and speaking to the surface through signals we're learning to hear. What we hear next depends on how well we listen. Even with every improvement on the horizon, there are things about the core we will probably never see directly. That limitation is worth sitting with, because it shapes how all of this research is framed. We will almost certainly never send a probe to the core. The engineering problem is not just difficult, it is, under any technology we can currently imagine, impossible. No material we know of can tolerate the temperatures, pressures, and chemical conditions at the core mantle boundary, let alone survive the journey through the mantle to get there. Every proposal that has ever been made for a core-penetrating probe has relied on speculative physics or materials that do not exist. For the foreseeable future, the core will remain the one place on our planet that we can only study remotely. This means we will always be working with indirect signals, seismic waves, magnetic measurements, isotope traces, theoretical calculations. Each one is a window, and each window has a specific shape. We can combine them to build a coherent picture, but we can never verify that picture against direct observation. This is different from almost every other object in science. We can fly to the planets and send probes to sample them. We can collect rocks from asteroids and bring them home. We can build telescopes that resolve distant stars and galaxies in extraordinary detail. But for the inside of our own planet, we are permanently stuck at one remove. That is a humbling thought. The most important object for our own existence is the one we can never touch. It also means that our understanding of the core will always be provisional in a specific way. Every model is subject to revision. Every conclusion is a best fit interpretation of indirect data. When new techniques emerge, old conclusions sometimes have to be overturned. The Superionic result is a perfect example. For nearly a century, every textbook described the inner core as a solid. Now that picture is being rewritten. It is possible that in another century, future scientists will look back at current models and see them as quaint first approximations. That is not a failure of science. It is how science is supposed to work. The commitment is to follow the evidence, update when new data arrives, and maintain honest uncertainty about what we do not yet know. In the case of the core, that uncertainty is substantial, and it is not going to vanish in our lifetime. What we can do, and what the last few decades have done remarkably well, is tighten the picture, narrow the range of possibilities, rule out the simplest models, replace them with more structured, more dynamic, more coupled ones. The core we understand today is a vastly richer object than the one we understood in 1990. The core we will understand in 2050 will be richer still, and so on, for as long as the discipline continues. In some ways, the inner Earth is now what the deep sea was a century ago, still mysterious, still only partly mapped, but no longer unreachable to the imagination. Every year more of it comes into focus. Every discovery invites the next question. The most important thing we can say honestly is this: the core is active, coupled, dynamic, and surprising. It is not what we thought it was. What it actually is remains an open problem, and the work to answer that problem will outlast every current researcher in the field. Which brings us to the final question. What does all of this actually mean for us in the long run? Everything in this story, every chapter, every finding, every data set, points toward one conclusion that older generations of geologists and geophysicists would have resisted strongly. The Earth is not a layered stack. It is a coupled system, and the coupling is far tighter than anyone believed. Start at the center and work outward. The inner core is not a frozen sphere. It is a slowly growing, possibly superionic, anisotropic, shape-shifting body whose surface is being deformed by the turbulent outer core above. The outer core is not a simple convecting liquid. It is a complex three-dimensional flow system whose patterns are shaped by the structure of the mantle pressing down from above and the inner core pushing up from below. The core mantle boundary is a region of chemical exchange where material, in small amounts, passes from one domain to the other over geological time. The mantle above is stirred by convection cells whose shapes are influenced by what the core below is doing. The magnetic field that emerges at the surface is a direct product of all of this deep activity, and its regional variations reflect specific features of deep flow. The atmosphere, the oceans, and the biosphere, through mechanisms we're only beginning to understand, linked to all of it through long-term feedbacks. Every layer talks to every other layer. Nothing is isolated. This is not a return to old mystical ideas about a living Earth. It is the opposite. It is what the hardest quantitative data is telling us. The planet functions as a single, coupled, slow-running engine with many moving parts, and each part responds to changes in the others across timescales, ranging from milliseconds to hundreds of millions of years. For most of human history, this engine ran in a mode we took for granted. A stable magnetic field, a predictable length of day, reliable regional climate patterns, steady ocean chemistry. It was easy, under those conditions, to imagine the solid Earth as a fixed backdrop to life, rather than an active participant in it. The evidence of the past few years has made that picture untenable. The inner core is changing. The magnetic field is restructuring. The atmospheric composition has deep ties to what the core does. The backdrop, it turns out, was always moving. We simply lacked the tools to see. The practical consequences of this for our lives are modest on short timescales. Nobody alive today needs to worry about a magnetic reversal. Nobody needs to rearrange their life because of the inner core slowdown. The shield above our heads is strong enough to keep doing its job for the rest of our lives and for many generations after. But the consequences for how we think about our planet, how we teach it, how we plan long-term infrastructure, and how we frame our place in the universe are profound. We live on the outer surface of an active engine, not a static rock. The engine has been running for 4.5 billion years. It will keep running for billions more, and along the way it will continue to shift gears, send signals upward, and occasionally surprise whatever civilizations exist at the surface at the time. The warning signal the core sent us is not the start of a disaster. It is the start of a new understanding, a reminder that everything beneath our feet is connected, moving, and alive in ways worth paying attention to. The planet is speaking. We are at last learning to listen.